Hello and welcome to the chapter 15.3 lecture on partial derivatives. So partial derivatives will be a function of position plus direction. The direction is a unit vector, and it will give the slope from that position in the given direction. So a nice way to think about this, look at this guy. If he goes in different directions, there are different slopes, and the slope in a particular direction is the partial derivative in that direction. So along this way, the partial derivative is positive, while along this way, the partial derivative is negative, decreasing slope. So here's the rigorous definition. The partial derivative with respect to x, we use this del symbol for partial derivatives. So in single variable calculus, you used ddx. In multivariable calculus, we'll be using del x, and this indicates that it is a partial derivative of a multivariate function. And remember that this sign means evaluated at AB. So the partial derivative with respect to x of f of xy evaluated at AB. Another notation for this is del f del x evaluated at AB. And yet another notation is f sub x evaluated at AB. And it is the limit as xy approaches AB of f of a plus h comma b minus f of AB over h. So the important part, look at this part. The b does not change. We're only looking at a change in the x direction. So it is the single variable definition of a limit, but applied only to the x component. And likewise for the partial derivative with respect to y, all the same notation, just now you have y's. And now we only change y and keep x constant, and that makes it the derivative in the y direction. So here's some visualization of partial derivatives and what's going on in this definition. So the partial derivative with respect to x, that means that we hold y constant around the point. Here's the point a comma b. If we are holding y constant, then y is just constantly b. So it's like this slice of the surface that we're taking kind of the single variable derivative of. So we hold y constant and we let x get closer and closer to a, and then this tangent line will ever more approximate the slope in the x direction at this point, as indicated here. And similarly, for the partial derivative with respect to y, we hold x constant. That takes a different cross-section of the surface, and we let y approach, the y component approach b, and that tangent line will ever more become the tangent to the surface going in the y direction with respect to its y coordinate. So how do we actually compute these partial derivatives? Well, in computing del f del x, we treat y as a constant and take the derivative with respect to x in the calculus one way, and likewise for del f del y. So for example, let's find del x of x squared e to the negative y and evaluate it at this point. Okay, so first, this guy. Del x of x squared e to the minus y. We can think of that. So we're holding y constant. And that means that if it helps you think about it, you can imagine that y is the number 5. So if it were the number 5, then it would be dx of x squared times e to the negative 5. And then this whole guy is constant. So if there's a constant times x squared, then it's just 2x times that constant from calculus 1. And in the same way, so we imagine that y is 5, and now this guy, that means that the partial derivative here is 2x times e to the negative y. So again, y was a constant, just imagine that it's 5, and take the calc 1 derivative. And then to evaluate it, at the point, 2, 0. That means that we just plug in 2, 0 into what we found here. So that's 2 times 2 times e to the negative 0, plugging in, and we have 4. So I encourage you to pause the video, try your hand at both of these. Okay, so del x of sine xy, that will be, so we're imagining that y is a constant. So imagine it like sine of 5x. That means that we would pull out the 5 and make that a cosine by the chain rule. So just as we would pull out a 5 in sine of 5x, we pull out that y, and we have y times cosine of xy. And similarly here, del y of this, that means that we are holding x constant. Once again, imagine it like sine of 5y, and we're taking d dy of that. That means that we pull out the x, and that is x times cosine of xy. So again, for this part, imagine it like d dy of sine of 5x. That would be 5 times cosine of 5x. Since we replaced the x part with the constant, and that's what this is. Here's another example. Let's find del x of this guy. Okay, so we're imagining that y is a constant. So let's imagine it as being like dx of e to the negative x squared minus 5 squared. How would we take that derivative? Well, we can separate it into 2 parts. That's e to the negative x squared times e to the negative 5 squared. Now this guy is just a constant, so it just sticks around in the derivative, nothing happens. And this guy, we would, by the chain rule, pull down the derivative of negative x squared. So that's negative 2x times e to the negative x squared times e to the negative 5 squared. And if we want, we can rearrange that as negative 2x e to the negative x squared minus 5 squared. So remember that 5 was just a substitute for y to help think of it as a constant. So we have negative 2x e to the negative x squared minus y squared. So once again, I encourage you to pause the video and try to find both of these. Okay, so this first guy, think of it, so we're taking del x. So we think of it like d dx of 5 squared, making y constant, and that would be 0. So that's exactly what this is. Del x of y squared is 0. While this guy, so that would be d dy of y squared when we make x constant. There is no x to make constant in this, so making x constant, to imagine it, changes nothing. And that would be 2y. So therefore, del y of y squared is just 2y. Now we can take higher order partial derivatives. Just as in Calc 1, you could take second derivatives or third derivatives of functions. It's just doing the derivative twice, except now we can take, for example, del x of del y of f. So that means that we would first take the partial derivative with respect to y, and then take the partial derivative of that with respect to x. And we have compact notation for this. So del x of del x is del squared f del x squared, just like in Calc 1, d squared f dx squared. Similarly for y, and if we have a mixed partial derivative, then the order, well, we'll see it doesn't really matter in most cases, but del x of del y, that'd be del squared f del x del y. So the x part partial derivative came second, so that would go first since function composition is right to left. Likewise here. And we have our alternate notation. I won't be using this notation, but almost ever. But sub x, that means with respect to x. And if we take the partial derivative twice with respect to x, that would be f sub xx. Likewise with y, and likewise with mixed ones, f sub y sub x, derivative with respect to y, then derivative with respect to x is f sub yx, and likewise. Oh, and what we say would be here df d squared f d squared or f sub xx for either of these notations. They're the same thing. So let's do an example of a higher order partial derivative. So I'm going to stop doing the substitution with 5 at this point. So first we have that del x of sine xy. We did this earlier, that is y times cosine of xy. And now del x of this, we're taking the derivative with respect to x twice. Okay, so this y on the outside is a constant, so it just hangs out there, and we pull out another y, and by the chain rule, and now derivative of cosine is negative sine. So we have negative y squared sine of xy. And let's do a couple of examples of mixed partial derivatives. Let's take del squared del x del y of sine xy. Okay, so for that, first we would take del y of sine xy. And that is equal to x times cosine of xy, since x is constant, pulled out by the chain rule. And then we take del x of this guy. And for this, we need to recall the chain rule. So recall that the derivative of f times g is f prime g plus f g prime, except now it's with respect to x for both of these. Derivative of x with respect to x is 1 times g plus f, that's x, times the derivative of g, but this derivative is with respect to x. So we pull out that y by the chain rule and make that a negative sign. So we have negative y sine of xy. So that's cosine of xy minus xy sine of xy. Now this guy. So that means that first we are taking del x of sine of xy. That is y times cosine of xy. And then we are taking del y of that. Once again, we need to recall the chain rule, except now here it's with respect to y. Derivative of y is 1 with respect to y. And then we have cosine of xy. And then plus y times the derivative of cosine xy with respect to y. Now x is a constant, pull it out. Derivative of cosine is a negative sign. So we have negative x times sine of xy. So that is cosine of xy minus xy sine of xy. Now look at this. We got the same thing. So del squared del x del y of this function was del squared del y del x, switching the order. That's not a coincidence for just this function. It is the Clairaut equality of mixed partial derivatives. It says that if f is defined on an open set D of r squared, which in practice usually means almost all of r squared, just any function really, where the derivative makes sense. And if the two mixed partial derivatives are continuous throughout that region, which will again basically always be the case in this class, then the mixed partial derivatives are equal everywhere in the domain. So in other words, pending continuity within the open set of the function and its derivatives, then del squared del x del y is del squared del y del x. So we can always switch the order and it is the same thing. Practically speaking, since all the functions that we're dealing with have derivatives which are all continuous as well. Now we can also take partial derivatives in 3 or more variables, and it works exactly the same. It means that now we are imagining that every other variable other than the one with which we're taking the partial derivative is a constant. So here we might imagine that it's something like d dx of 5 times x squared plus x times 3 squared plus 3 times 5 squared. If z is 5 and y is 3. So we would imagine taking that partial derivative, or that single variable derivative, and the result when we back substitute 5 for z and 3 for y is that partial derivative. So if we did this, well, that would mean that then d dx of this guy is equal to 2 times 5x plus 3 squared plus 0. Okay, so that means that this guy is 2zx plus y squared, full stop. Now, having partial derivatives in the x and y directions is not sufficient for a function to be what we will call differentiable. The underlying idea of differentiability of a multivariate function is that the function is locally approximated by its tangent planes, whose slope in the x and y directions are f sub x and f sub y. So to this end, we defined that a function z equals f of x, y is differentiable at a, b, if the partial derivatives exist, and the change delta z equals the partial derivative with respect to x times the change in delta x plus the partial derivative with respect to y times the change in delta y plus vanishingly small errors in essence. I think that a picture would help this. So here's a surface, and here's the tangent plane to that surface at this point. We say that the function is differentiable at this point if it's arbitrarily well approximated by the tangent plane in all directions. So in Calc 1, a function was differentiable if and only if its tangent line was an arbitrarily good approximation as you approach the point. In multivariate calculus, now instead of tangent lines is tangent planes. So the tangent plane is a linear approximation to the surface at that point, just as tangent lines were in Calc 1. And that concludes this other short chapter. This is why I assigned 3 chapters in 1 week. Have a great one.